Works. Yeah, hi, good morning, everybody, and welcome to this workshop. I would like to thank the organizers first for creating this opportunity for us to gather together here and then to interact and discuss and so on. I hope everybody is going to enjoy this. I'm Mina. I am representing SynSense, and today I will talk to you about neuromorphic embedded intelligence for seamless robotic interactions. So the order of content that I will cover is first I will introduce the company and our technology stack, and then I will have a high-level overview of neuromorphic sensing and processing technology in robotics with some concrete examples from the applications that have been used from SynSense and innovation products in robotics context. At the end, I would like to open some discussion about some challenges and challenges and limitations, and eventually we will have a glance to the next generation of neuromorphic solutions. So SynSense is a spin-off of INI, University of Zurich and ETH Zurich. It was founded in 2018 in Zurich. Professor Giacomo Indeveri is our co-founder, and then that's how this SynSense inherits more than 20 years of experience, R&D experience from the academia. We have offices in Zurich and in China. I probably have to move this. This is creating a bit of issue, but not really.
Click here in this little bar here. What is it? Here, when you have the bar here,
Yeah,
you just click in this mini
I'm just
line there.
looking for. Yeah.
Yes, it's difficult to find the mouse, but now there we go. Perfect.
Okay.
So it's less and more.
Okay, let's go back. Okay, I'm sure it's better now. Okay, yeah, we have offices in Zurich and a few offices in China, and SynSense is the world leading supplier of neuromorphic intelligence and solutions, and we cover both sensing and computing, neuromorphic sensing and computing technologies. And I'm sure many of you know Innovation as well, another neuromorphic startup in Zurich. Since last year, SynSense acquired Innovation, so we have joined forces. Innovation is the world leader in neuromorphic vision solutions. They also have similar roots to us. They also were a spin-off of INI, University of Zurich, more or less with same co-founders and people involved, and with a large portfolio of various event-based sensors and a very active and open source software that is widely used in the community, and with a large number of customers and partners and collaborators across multiple industries. So SynSense was mainly focused on neuromorphic processors, and since we acquired Innovation, now we are covering both neuromorphic sensing technologies and processing. So SynSense covers two main line of products in neuromorphic processors. Some of you may know and have used this. SPEC and Xylo, both of them are manufactured in digital technology. SPEC is integrated, actually the only integrated DVS camera chain with the SNN processors. It is what you see at the left is the SPEC module. It's very small. Unfortunately, yeah. Yeah, so yeah, worse. So this module is actually placed here, and the rest is the dev kit, basically what facilitates users to build applications on that. But the module itself is that small. It is suitable for gesture recognition, visual object tracking and recognition, and that kind of tasks, and with very low power consumption. Xylo, on the other hand, is much smaller. It contains only 1,024 neurons. It has been on contrary to the SPEC, which is a spiking convolutional neural network, Xylo is a spiking feed-forward kind of network that you can implement. And it is suitable for natural signal processing and including audio and IMU. And distinctly, we have developed a front end for audio processing and IMU processing for Xylo. So let's see how this technological components fits in robotic scenarios. For a solid robot design, one needs to have a controlled motion, controlled force, and controlled behavior. And this all require having high quality sensors and reliable sensing and processing hardwares. And for example, for controlled motion, one needs to have efficient scene analysis methods, real time and with a manageable power, along with inertial sensing. And for acoustic perception, for tasks like keyword spotting and source localization, for the robot to understand what is being asked, what's the keyword, and also what's the source who is asking that. So this will result also to the controlled behavior of the robot in a very simple view. And for having the controlled force, one needs to have efficient tactile sensing sensors and algorithms, for example, to accomplish the tasks like texture classification and slip detection and so on. Neuromorphic solutions fit very well in these scenarios, and in the next slides, I will have some examples of our products used in these scenarios, including SPEC, the vExplore, and Xylo. So just another quick review of what is the specification of each of these. SPEC is a 128 by 128 DVS camera chained with SNN processor. vExplore is a VGA resolution DVS, and Xylo is suitable for is a SNN processor with audio and IMU front ends, suitable for time series analysis and so on. For SPEC, as I mentioned, the typical use cases are low power and always on monitoring of motion and environment, kind of rare behavior detection, gesture recognition, and so on. And I will go through, I will review two key examples from two recent works. One from Julia, event-driven visual attention by inspired visual attention. And the other one is a very nice work from Queensland University of Technology. So the first work is a simple yet elegant work, end-to-end neuromorphic. So they have mounted SPEC on a pan-tilt device, and basically the device is using the saccades, using the ROIs detected by the system to use saccades and have efficient navigation. It is composed of object motion sensitivity part and proto-object detection, which the first one is sort of receptive field filtering with Gaussian centers that basically reduces the number of events and finds an early ROIs and then passes it to SNN that is detecting the proto-object and eventually a saliency map and eventually a pixel XY sent to the control of robot and to move the pan-tilt towards the most interesting parts of the scene. So here is a video that shows that. So the stream of events, raw events coming from camera in the second panel in the right, you see the object motion sensitivity map, and the other one is showing how much the amount of events are reduced to find the most salient parts. So this kind of works, not only it's very interesting from scientific point of view to show an end-to-end spiking platform to do experiments and also to extend it to many other functionalities. And as far as I know, Julia is extending this work with many other ideas. But also from the industry point of view, it is interesting because it provides a simple but very reliable component to be integrated in more complex navigation and tracking systems. The second showcase that I will mention is this very nice on-device visual place recognition. If you were in the session on Monday, event-based SLAM session, if you were present there, Tobias nicely presented this work. It is basically, they have integrated our spec in a hexapod robot, and they have used it for visual place recognition task. The whole system is very compact, and the whole the network, the train network, is very impressive, very small. So versus all these huge modern SNNs and transformer-based networks that are used currently in the modern SLAM systems, this one is really a very small network. Altogether, the model size is not more than 180 kilobyte, and it includes about 44K of parameters, and it uses about 8% of conventional power of conventional platforms in comparison with Jetson, for example, here. This is very promising, and it's a great and elegant example to show the community that end-to-end neuromorphic low-power applications are basically working in practice in a very real setup, real-time, low power, and with a very competitive accuracy benchmarked against other methods in the field, and covers small scale and large scale indoor and outdoor visual place recognition tasks. And very nice documentation, everything, repo and everything is open source and well documented. I encourage you, if you're interested, to go through it and check it. And the next examples will be with DV Explore. Two main examples here I will cover. One is IFTAC. It is event-based tactile sensing. And the other one is Foveator Track. It is a fast and precise ID-based tracking from ourselves, from innovation. And the first one is from researchers from University of Darmstadt and Technical University of Dresden, a paper from last year. So IFTAC is also a very nice and promising example. Optical tactile sensing is in general very popular. It's a very elegant and simple solution, and it basically integrates a layer of elastomer combined with a dotted array with the RGB camera. So the idea is that this would be placed on a glove or on a finger sensor for a robot, and any touch and any force will deform that gel structure, and that deformation will be reflected in the motion of the dots, and the camera will track and basically classify that pattern and assign it to a certain force or certain texture and so on. So this is very nice working setup, but as you know, like all frame-based systems, it suffers from low frame rate and also high amount of data. For example, it keeps sampling the surface when it is not necessary, even when there is no change, and also the sampling rate is not sufficient to cover scenarios like certain vibrations or some slippage and so on. So with this motivation, the researchers from University of Darmstadt and Technical University of Dresden. And I guess yesterday they had a nice keynote session presenting this work and some others. I personally missed it, but I hope some of you attended that. Yeah, they have basically replaced this RGB camera with DV Explore camera from Innovation to overcome the shortcomings that the system has. They have reported very nice performance in texture classification, being able to classify a wide range of materials, being from wood to plastic or a wide range of materials, and also very significant effectiveness in sleep detection, actually in a scenarios that frame-based camera would totally fail. So in fact, the millisecond resolution of DV Explorer here enables sort of even early detection and prediction of the slippage of the object in the hand of robot. So this is very useful for controlling the force and doing something before the robot drops the object or something. And the other example for Viator Track is also interesting from the, let's say, larger scale robotic control and interaction control. What you see in the cartoon in the right is several robots in a large space playing, interacting, moving, and the ceiling is covered with a good number of cameras to cover their motion. So in fact, every robot is covering a LED marker on the head, and LED markers of each robot is sending a binary code very unique to that robot, which is detected by DV Explorer with that precise millisecond resolution. So as such, the system is able to track each robot and identify who is where. So this can be used in let's say in scenes when there are so many industrial vehicles, robots, or even people. And this brings me to another example that one of our customers, in what you see in the right picture, one of our customers used this system in a gaming facility for interactive gaming in an entertainment center. So people or kids, they would wear a hat with these LED markers on the head. So the system, based on the rules of the game and based on their interaction, their speed, their position, would score them. And this is a basis basically for designing many interactive games. In fact, by mixing it with the right graphics and making it appealing and so on. And last but not least is some nice examples and use cases from our Xylo. Ourselves have had several internal demos, also papers for keyboard spotting with Xylo, and also a recent paper from sound source localization. So this can be a joint solution, basically for keyboard spotting and sound source localization, and can be adapted for robots and integrated in robotic systems. For inertial sensing, we have not integrated in directly on robots, but we have some examples of customers who used our Xylo IMU for animal behavior detection or basically livestock monitoring and scenarios like that in the form of smart ear tags, smart collars, or smart leg bands. These use cases also can be easily adapted to change the to detect and analyze and monitor the orientation of robots and in similar scenarios. Okay, so this is all very cool, but I would like also to bring some food for thought for maybe for our debate session. Of course, always there are challenges, and I'm sure most of you, if you have been long enough in Neuromorphic, will agree, and maybe you will add some more to this. So one challenge is that the cool technological advancement doesn't translate fast enough to wide industrial adoption. There are many reasons for that. Maybe one can be the high cost of neuromorphic solutions, and it is because they have a specialized manufacturing. They're not very mass production, and they're expensive because of that. So hopefully by simplifying the designs and bringing designs for a more mature state, this problem of cost will be solved. But another undesirable consequence of this slow industrial adoption is the slow and sparse feedback that we may get from the customers, because as a company, we love to get to hear the experience of customers, to see what they think about that, if they found a limitation or bug. And the more customers, more users, it's great for us. So this is currently additional effort for us to reach out to do special, basically to do additional effort to get their feedback and experiences and so on, which hopefully by growing the community, this will be solved. Another one is that even though the neuromorphic community is not big, it's actually very small, but there are lots of fragmented and redundant efforts. So yeah, this is another, like, this can be a session for itself, but yeah, we would also like to align those efforts. And there have been some very good steps in good direction, like last year or in the few past years, there were some challenges, event-based challenges in CVPR. So this is sort of for eye tracking, for example. This is very nice alignment. Another nice example is Neurobench efforts that tries to define standards and so on. That yeah, I hope all this continues, and it requires effort from everyone in the community. And another one for us as a company is a dilemma that we have at the design level. After we get all this feedbacks from people, or people that keep telling us, oh, it would be cool to have this feature, this or that. But eventually in a competitive market, these are high risk decisions for us to take. That, for example, let's say, should we design a targeted, specialized hardware, or we stay at the general purpose solutions and so on? This kind of yeah, dilemmas also exist. After all that being said, I will give you a glance to the next generation DVS that we have designed, and hopefully it will come out. It will be released early next year. Compared to legacy event-based sensors, this we call it Avion next generation. It has a simpler digital technology and modular design. It uses the standard pixel arrays and has in-sensor comparison. It has hybrid operation, meaning that you can have normal legacy event-based output with binary or gray level events, but also frame-based compressed efficient output. The output goes to a maximum of 1 kilo FPS. And more importantly, what we are most excited about is that we are redefining events. We are introducing new advanced event modes, that events, instead of being incidents in the pixel level to tell you where and when a change happened, now you will have them at macro block, some higher level information at macro block level. So in fact, this way we are using we are taking advantage of not only sparsity in time, but also in the space. And here I will show you two videos from this representation. This one is, okay, okay, this one is basically a rich feature that we get from that compressed intermediate representation without any effort to to basically reconstruct the image. This representation is about 5 to 10 times more compressed from the original image, and also from the reconstructed one. So from our first results, it sounds very promising for many tasks in which you may not need really actually to build the full image, this representation may be enough to offer a low power solution for applying many algorithms on that and fulfill the tasks without reconstructing the full image. The other one is, oops, okay, is this low-level motion information that I mentioned. So what you see here is this eye move. This is a very fast blink. In fact, it is about 200 milliseconds. I have slowed it down like 40 times or so. So for that very fast blink, you get constantly this, at the sensor level, we receive this low-level motion information that can be a great basis for optical flow and motion-related tasks, and basically eases the modeling and so on. So currently, these results that I'm showing is from the simulator. As I mentioned, the sensor will be released next year. Currently, we are releasing the simulator to some academic and industrial partners to explore and do experiments with that and get ready for the real sensor. So if you are interested, please let's talk and so on. I'm available. Yeah, I think that's all. Thank you for your attention.
Thank you very much, Mina, for the talk, for showing perspective from industry. I guess while Luna is setting up for the next speaker, we probably have one questions.